should announce it. It doesn't announce it. Not hearing anything, turn up the volume. It's like pretty useless. This is. Right.
All right, someone's there.
Yeah, Amani's there. He's got a kid. He's gonna be home with his kid. So we got you here. So it should be okay.
Yeah, fire it up.
So I think it's running. Let's make sure it's recording. Yeah, it says pause, so it has to be recording.
Yeah,
Right?
yeah.
I went a couple times it didn't. So you guys, thanks for coming. We got Ben Yavitt here. He's a professor in chemical engineering. Maybe you guys, anybody know him or? Oh,
I had a few of you guys in
okay.
class, yeah.
All right, so he did before he came to UC, he did work at the Brookhaven National Lab in New York, and he did this XPCS measurements. So he's an expert at it. So I thought since we kind of came up to that in the class notes, like for the resident expert, he could say stuff about it.
Yeah.
Then you could ask him about stuff about that and about, I don't know, anything, basically.
Well, not anything.
He's kind of he's a rheologist, basically. And he worked with Henning Winter. It's like the guy that invented gel rheology, more or less, like how you understand that. And then what else? And then he's here, professor. So
did you guys study rheology yet? Did you go?
yeah, oh yeah, we've gone through extensive. We do like a paper.
Okay, cool.
Probably more than half are about rheology.
I'm sorry, I didn't look at
so,
the syllabus or anything.
Yeah.
So.
No, all right. So let's see. Are you gonna? Let me get my pens out so in case you want to mark something. A couple pens.
I have one.
Oh, you do?
Yeah, yeah.
Oh, okay. All right. All right. So ask questions. So they'll interrupt you.
Okay.
They get 20 points a question.
Ooh.
Now you get only 20 points per class if they ask a question.
A question.
Those are
Okay,
my
great.
questions. So they're motivated for questions.
Did you guys?
You could ask a question right now, like why are you wearing that shirt or something?
Okay. Why am I wearing this shirt? It's cold out. I don't know. It's the first one I grabbed out of my drawer this morning. My other question was, did you guys see the papers yet that you posted?
Yeah, well, no.
Okay.
Yeah.
So I wanted to.
That's like next week. That's next Monday's homework.
That's next Monday's homework.
Yeah.
It's due next Monday.
Yeah. So
Okay.
they won't work on until the weekend or something. But there's
Obviously.
Yeah.
I just wanted to pull them up because they are
okay.
If we have time, we can talk about them. So
Yeah. So there's this is the paper with
yeah, we can do
Weiger.
that one first.
And then
Do that one.
this one is, I haven't put the supplemental up
Okay.
yet. This is a reference to, he's got a theory for the mechanical behavior.
Yeah.
That's his theory.
That's the theory. Okay.
And this thing, oh, that's the model. Reference 72 is, you know what that is, right?
Yeah.
Okay. All right, so they're all there.
Okay. Because that'll help explain the experiment.
Yeah.
There's one more I wanted to look up. Was what's this guy's name? Yeah, so I'm going to talk about the experiment that we're going to look at today, and then go through a few papers that explain some kind of cool behavior with them. So Greg picked out a few, and I have a few other ones that I think are really interesting and useful to look at. But today, really what I want you guys to start thinking about is where my PowerPoint went. There. So I understand you did light scattering last week or no, 2 weeks ago. Yeah, so you did dynamic light scattering before spring break. So I'm assuming you all forgot it over last week completely. Okay, so the technique we're going to talk about today is essentially dynamic light scattering. It's basically the exact same thing, except now we're using X-rays instead of a laser light, all right? So with dynamic light scattering, you were shining a laser at some solution, so suspension, some polymer structure, and trying to see what that structure was, right? Does anyone remember what the wavelengths were of the laser light that you might have used? What kind of length scales were we talking about?
don't you guys could guess?
Yeah, I guess. What's a laser pointer? What's the wavelength? Blue light. Okay, great. Do you remember what the wavelength of that is? Perfect. Yeah. So a laser that you use for light scattering shines light at a wavelength of around 400 to 500 nanometers, something like that. And when that interacts with your material, the length scales that you can look at are on the order of about microns. All right. So those are kind of the structural length scales we're looking at. Does anyone know what X-rays are, what the wavelength of an X-ray is?
Aren't they much shorter?
Way, way shorter. Yeah. So when you use X-rays, they're much higher energy and much shorter wavelength. 0.1 nanometers, something like that. Yeah. So that's an order of about 0.1 nanometers. So thousands times smaller length scale that we're looking at. So when you use X-rays and you shine that at your sample, we're talking about Q space, that reciprocal space that we can measure in. Now we're starting to look at things on the angstrom to nanometer length scale. All right. So light scattering is really good for kind of big global structures you want to look at. If you want to look at really small things like nanoparticles or nanoparticle dynamics or small polymer structures, you have to go and use X-rays. All right. So that's what this technique here is. This is get rid of that thing. This is a analogous technique to dynamic light scattering, and it's called X-ray photon correlation spectroscopy. And we're going to talk about it today. All right. So this is what I did for my postdoc. And basically what you do is you still have some sample right here with some structure. So in the case, usually what we're looking at is like nanocomposite materials. So you can think of things like rubber, which have little fillers in them, which hold the polymer structure together, or any other type of engineering plastic where you add in nanoparticles to make it stronger. We want to understand what the structure and the dynamics of those particles are on that nanometer length scale. All right. So what you do is you shine that X-ray at that sample, the X-ray hits it, and then scatters off as it interacts with all those materials. All right. Now behind it, what we have is the detector. And what you see on these detector are these kind of crazy patterns with a bunch of dots. Does anyone have any idea what that's called? I have it listed on my slide. That's actually called a very scientific term. We call that a speckle pattern. And it's literally just a collection of all the photons that came flying out of the sample and landed on the backside of the detector. And what this speckle pattern does is it's essentially recording the instantaneous structure, the instantaneous arrangement of all those particles at one instance in time. This X-ray beam is so high energy, so fast, that it just goes through and it plops up, and it can basically record that spatial orientation of those particles inside the sample at that one moment. All right. Now, what we do is we take a series of these speckle patterns over and over and over again over time. And what that does is you then see the very abrupt kind of local motion and translation of those particles. All right. So this is essentially just a movie or a recording of those particles moving around now on that nanometer scale. All right. Any questions so far? Does this remind you of dynamic light scattering? Dynamic light scattering is the same thing, right? You're looking at the intensity in time and seeing how that changes. But now what we're doing is we're actually collecting all the intensities on the back of that detecting pattern right there, right? Yeah, Brandon.
How do you know which particle matches with which particle?
You don't. That's the thing, right? So this is a real space process that's happening, things moving around in space. But what we're getting is a reciprocal space pattern of that behavior, all right? So the data we get here is now intensity in terms of the scattering vector Q. You remember the scattering vector from light scattering? It's that inverse length scale that you're probing at, all right? So that's the thing. We don't know what's going on there. We're trying to inversely understand how these things are all moving around. But the cool thing about this scattering detector is as you go out further from the center, that looks at different Q values or different Q spacings, right? Remember the angle from your light scattering setup told you kind of what length scale you're looking at. So what we do here is we have this full detector, this huge pattern, and we can go and isolate it and look at it at different Q values. And we basically just watch the intensity kind of variation change in time, right? You guys went over this with light scattering as well? Right, Greg?
Yeah.
Okay.
Yeah.
So remember, when you're looking at light scattering, what you're watching is how the intensity at some location fluctuates in time. What we're doing in XPCS is we're doing that same type of measurement, but we're doing it at like thousands and thousands of pixels across that detector. We're basically doing a dynamic light scattering experiment like 1,000 times, but we're doing it all at once. And what that allows you to do is you can now look at different Q vectors. So you can zoom in and kind of understand what's going on a small length scale, as well as blow up and look at on a big length scale.
DLS just has one detector. right?
Yep, DLS just has one detector.
It's kind of because the geometry is a little bit different, like the sample's in a tube.
Yep.
So you shoot the beam through, so you can only collect, so it has to come out the same, it goes to the middle of the tube and it has to come out, so it's in the middle of the circle. You can only detect around that way. Can't detect like that way with DLS. Basically, it's a sample geometry.
Yeah, so with light scattering, you had your detector off at your one detector off at some angle, and you were watching the intensity change in time. With XPCS, we're basically able to pull that detector over all the angles
So the other
on
thing
this
is
2D
that
scattering
light's
pattern.
really sensitive to dust, because dust has a huge index of refraction.
Yeah.
When it's solvent it's in, they usually kind of things in solvents and light scattering. But in getting the dust out, so if you have a polymer, roughly the size of a polymer is about the same size as the size of the dust. So you can never get a clean polymer, like you can't filter polymer. Basically, you have to deal with that in dynamic light scattering.
Yeah.
The dust kills you. All you see is like dust. Luckily, dust moves slowly, so you can kind of discern the dust from the motion of the polymers faster. But X-rays are nice because it's electron density, and there's not much dust that's made out of lead, or uranium.
Yeah.
Basically, it's cleaner. It's a much cleaner measurement to do.
So yeah, I'll talk about it, but we can take industrial materials, we can take model materials, you can literally take whatever you want
So you could never do that.
and throw this into the X-ray beam and get pretty good data and pretty
And you
good
can tune
measurements.
the synchrotron, you can tune the energies, you can get the energies.
Yeah.
So the higher the energy, the more penetrating. You can actually put a chunk of steel from an engine into the X-ray beam, get diffraction.
Yeah.
This kind of measurement. You could never do that with light.
Yeah,
Or
I've
you just
seen
walk
I've seen a lot of folks work on battery materials as well, with a lot of like high density inorganic material, kind of see how those structures behave and how they're evolving under processing. So
X-rays are cool, like, especially synchrotron, the flux is so high. The lab X-ray, like when you go to the dentist, so the flux on this thing is gonna be like 100,000 times brighter.
yeah,
More energy, not energy, but more flux.
Yeah.
More photons coming through. So it's incredible, actually. You can burn things in the beam.
like your hand.
Yeah, you can literally burn things.
We'll look at some pictures and talk about how we don't do that though. So yeah, so this experiment, again, just keep in mind, it's the exact same thing as dynamic light scattering, except with X-rays and over a little bit more length scales and behaviors. Yeah.
Feel this heat and satellites to make the solution.
Yeah.
Is it the same with this?
You can do this with solutions as well. Yeah. So a lot of people have done that to look at kind of diffusion of nanoparticles on the nanometer length scale. You do have to play around a little bit, like Greg was saying, with the flux, because this beam is a lot brighter and a lot stronger than a laser is. So sometimes we have to play around with kind of the energies and the intensity of that beam as we're going through, but you can definitely
Like,
do.
The first thing you do is, I mean, you showed us.
Yeah,
that.
yeah.
The first thing you do is like, you have to see if your sample burns or not.
Yeah, so every,
The dynamics you could be looking at are torching your sample.
yeah, so that doesn't happen with dynamic light scattering, but we always do a test. If your beam is too strong, your sample will just burn or basically deteriorate due to the radiation that you put on
So
it.
they have filters they put in to cut it back.
But yeah, anything you look at with DLS, you can do this with this experiment as well. But what it's going to do is now look at a different length scale of behavior, right? Remember, the DLS is looking at micron size type of motion and behavior. This is now going to zoom in and look at nanometer length scale type of behavior, right? Yeah.
Is there any requirement to maintain the sample transparency? Like, does it mean?
No, yeah. Optical transparency doesn't really matter, again, because these are X-rays, right? Light does whatever it does, but X-rays are so much smaller. We don't see X-rays. All you need to have is this good contrast between the two objects. So as I'm drawing here, the dots could be nanoparticles or colloids or something in suspension, like if you're looking at a solution. And then the gray part could be that background material, either a liquid or a polymer or something like that. And all you need is a good electron density difference between those two things. Because when X-rays come in, they're sensitive to the way that the electrons are distributed within the material. And if you have materials that have very different density distributions, that's what causes those X-rays to scatter. Yeah. Yeah. Oh, sure. Biological materials are not good. So again, because they can burn and get they can get deteriorated in the radiation. So there's not a lot of good studies with this instrument and technique using biological materials, but most polymers, metals, ceramics work pretty well. You won't know until you try. Again, you can bring it to the instrument and try and do the measurement and see what the dynamics are. But yeah, mostly you want kind of like a high, kind of a robust type of material. But I would say biological stuff is usually not that good. Yeah.
For traditional microscope, like the SEM, higher magnification does not determine better resolution. So I want to be sure if this works the same way with that.
Higher magnification does not determine better resolution. What do you mean by that?
Like the magnification, the way you zoom in, most times it becomes so noisy because you cannot properly see the samples.
Yeah, so
this, I want to be sure if this works the same way.
It doesn't quite work the same way because again, we're not looking at anything in real space. Like we live in the 3 dimensions of XYZ. We can walk around, we have length scales, right? We're not actually observing behavior in that space. We're looking at scattering patterns, which are in reciprocal space, right? This is some space that we do not exist in, we do not live in. So we're not really, I mean, you can use the analogy of zooming in and trying to look at something, but we're not actually observing that behavior with the instrument or with the technique. We're just resolving what that behavior is through a different space parameter. That kind of makes sense? But yeah, you do have to play around with the data and do really, one thing about this instrument, it's really easy to do the experiments. It's really hard to analyze the data. That's kind of the big limitation because you can get a lot of wacky things that might not make sense. So you do have to know a lot about your material ahead of time to make sense of the data. So yeah.
How do we distinguish between static and dynamic heterogeneities in sample?
Oh, that's a great question. I will come back to that because let's talk about how we analyze the data and we'll see how that behavior comes out. But that's a great point. Yeah. So yeah, the whole point of this is we're trying to look at the dynamics. Remember, in static or dynamic light scattering, you want to see how things are moving around in space. So in this same experiment, we're doing the same thing, and we're taking those intensity fluctuations in time, and we're calculating an autocorrelation function, which I know you guys went over last time, all right? It's the exact same type of process. You're looking and seeing kind of what the patterns in those fluctuations are in real time,
So
all right?
it's the same, it's at the same time they're perfectly correlated, so that has a value of 1.
Yeah.
If it's at times that are infinite apart, they're uncorrelated, so that has a value of 0.
So I kind of like this drawing. So
So long time delta t's, you get 0.
So if you kind of have a highly fluctuating system where the intensity is flapping all over the place and you try and draw those correlations together, you'll find that the intensity becomes decorrelated very quickly, right? There's not a lot of relationship between those intensities as you move along in time as compared to the beginning. So that's going to show a kind of fast decorrelation in your autocorrelation function, which means up here, structure intensities are matching. They're showing the same type of behavior. Down here, you've gotten to a place where those particles have moved off into another point, and their structure is no longer correlated with their original structure, right?
So it could be plus, it could be minus, and yeah, those up, it goes to 0.
Could be anywhere, yeah.
Okay.
So they're just not in the same place that they were before. So if you're watching a movie and nothing is changing in the scene, that means that is correlated, right? It's the same thing over and over and over again. But as you watch a movie and people start to move around and they go to different parts, obviously it looks different, right? It's a different structure, a different arrangement. That's what those scattering patterns are measuring. They're measuring how the structure is changing in real time, all right? So if you have a really fast system where dynamics are moving around really quickly, you have a lot of fluctuations, and that thing decorrelates very quickly.
Maybe this might be better. I don't know. If
You don't like my marker?
Yeah, well, these are colors.
Whoa, there we go. Okay. So if you have another system where the fluctuations are kind of not as strong temporally, there's much more correlation in those type of patterns that we're seeing from time to time to time to time to time. And in that one, you're actually going to then see a much slower process where the correlation function decays over longer timescales. All right. So those are what we're matching and trying to measure and actually calculate from these intensity functions. And the key thing here is this correlation function often follows an exponential decay with some characteristic timescale, tau. All right. And that tau is what we call the relaxation time. It's essentially how much time it takes for your structure to completely decorrelate or completely move to a new arrangement and a new orientation.
So you kind of get, for every Q, you gotta get one number.
Yes, so we do that measurement for every Q. No, it's not. So you do that at one scattering vector, basically looking at one length scale. So I have one area I'm looking at and I say, all right, how fast does it take for things to decorrelate? Then I go to another Q, which zooms out a little bit. And then I say, okay, how long does it take to decorrelate? And then you keep doing that across all the length scales from maybe 1 to 100 nanometers, something like that.
So it should drop.
It gets slower, yeah. So what we do is,
That's diffusion. That's
yeah, so you'll get a plot of the scattering vector Q and then that relaxation time that you calculate, and you'll see some trend like that there. Where as you get out to bigger length scales, that relaxation time gets larger and larger.
Mean square displacement goes with time, right? So you get a half square root time.
Yeah, or Q squared.
Or Q squared is time.
So this right here,
That means Brownian motion,
yeah,
which isn't what you always see. There's two kinds of motion.
yeah, we'll talk about that. So if you do that at a bunch of different length scales, you can calculate out the diffusion of that material because that space goes as, that time scale goes as Q squared. So essentially what we're doing with this instrument is measuring particle diffusion.
The bigger the relaxation time, the slower the motion.
Yes.
So it's kind of inversely.
Yes.
A big number is slow. Takes a long time.
Oh, sorry. Okay. Yeah. A long relaxation time is a slow process.
So the left is big, the right is small, so the big takes longer time than the other one. If it's diffusion, it goes with square root of time. The distance goes with square root. That's Brownian motion. Random motion. You can see it gets pretty involved pretty fast. It's a simple measurement, but already it's complicated. The simplest thing to do, you shine the laser at something and it moves around, it's like the cat chasing my doing.
Yeah, so that's the essence of the experiment. Again, exactly like dynamic light scattering, except we're doing it at different length scales and we're measuring across multiple Qs. Yeah, Krish.
Quicker, I guess the quicker the decorrelation happens, means that you have a steeper drop off when you're looking at the relaxation time, which means a steeper slope when you're looking at relaxation time over Q squared, which means faster diffusion.
It depends, right? So if you do that one experiment here, all you know is the relaxation time at that one Q. That doesn't say anything necessarily about the full Q dependence when you try and make this plot here. So something can be fast, but what you care about is how that time scale relates or scales with the length scale that you're looking at. Yeah, so that's what you'll see from these. So then you'll see ones that go maybe like that. Maybe like that, right? And the slope of that line is what's giving you the diffusion constant. So that's how you're actually measuring it out. It's not just to the time time scale at 1 Q, that's not actually that useful, right? You actually have to go look at all the Qs to figure out what that diffusion relationship is.
So then, I guess maybe a quicker diffusion would be that the slopes are like further scattered apart, like.
Yeah, things either slow down faster or slower as you get bigger and bigger, right? And if something has a fast diffusion constant, it's going to slow down slower.
And 1/d is the head of unit is from Einstein Stokes.
Yeah.
So, yes.
Did you guys learn that, the Stokes-Einstein relationship? Yeah. So that's usually what we're doing, right? So essentially this experiment is just proving the Stokes-Einstein experiment for very simple materials like that. So you know that basically as that thing's moving around, it's governed by its viscosity. If it has a low viscosity, it's going to move really fast.
That's if it's Brownian.
If it's Brownian motion.
All that stuff. He doesn't see it as.
Yeah, we'll talk about that in a second. How much time do we have? Shit, okay.
You know,
Yeah, so the cool thing about this experiment is that you can only do it at maybe 4 or 5 places in the whole world, I think. And that's because it requires synchrotron X-ray radiation. You can't just go to the hospital and use like whatever X-ray scanner thing they have there, right? This X-ray needs to be super high powered, super bright, super high flux, coherent, all these. Yeah. So you need a very perfectly well-defined beam of light to come in and hit your sample. Yeah. And so there's a few of these synchrotron facilities around the world. One of them.
And really bright.
Yeah, and really bright.
Yeah.
So what these do is this is a huge ring. This ring is about half a mile in diameter. No, it's yeah, there's cars there, right? So that's how big you can see. So it's about half a mile around, and it's a huge circular tube. And what we do is we
like for this turn in those places where they do particle acceleration and blast them together.
yeah,
There's one that they started to build here. I didn't zoom out to show it.
yeah, that one's huge.
And
It's
that
underground.
one's gonna be about maybe 8 times bigger than this thing.
Yeah.
So those particles, so this is a relatively small.
It's like a small particle accelerator, but it's not accelerating particles, it's accelerating electrons, right?
Or positrons.
Oh,
Antimatter
okay.
or matter.
But these ones are.
The APS is positron.
Is
I
it?
think this one's electron.
Yeah.
Yeah.
So what we're doing in this ring is you're injecting electrons into the ring, into this big loop. And then there's a ton of like a shit ton of magnets that are accelerating those and getting them all spinning around in a big circle. And you use those magnets to get them all lined up,
Because
bright and aligned.
Yeah, Maxwell's law, like you have a current and then you have a
Yeah.
magnetic field. So if you manipulate the magnetic field, you can make the current turn corners.
So
Go
it's
around.
basically just a huge stream of electrons flying around in a circle. And as they do that, as they're moving around, they emit light. So photons start to come off from that electron beam. And basically in each one of these buildings around the ring, we've got these little magnets that will bend and pick off some of that light. And that's your X-ray right there. So we've got this huge electron beam with just bright light going all over the place. And we're siphoning off the light in these tubes so that we can collect it and detect and project it at our sample and do this experiment. Yeah, you're looking.
Yeah.
Good
How's
question.
this process like managed? Is there people like watching it?
Yeah.
or-
This is a fun place to be because the number of scientists that work here is actually the minority. This is a scientific facility to do these experiments, but there's probably twice as many people, physicists and engineers, running and maintaining this facility. So there's like a 24-hour crew that's there all the time in the control room, making sure that all the magnets are at the right configuration, making sure that the beam is running at the right current, making sure that everything's operational. And then there's people running around doing maintenance on vacuum tubes. Do you have any pictures of what the inside looks like? Oh, it's a horrible picture, but whatever. Yeah, so this is a facility that's funded by the Department of Energy. So it's a government lab. And yeah, there's so many people just keeping it up. And basically the scientists just sit in these little rooms at the end and do the actual experiments. I'll be honest, I'm not a physicist. Don't really understand all the nitty gritty about how this thing works. All I know is that the light comes off and it hits a polymer and we can do something fun with that. So yeah. No, not at all. So that's the really cool thing about this. X-ray is used for all different types of experiments. So this is one type of experiment that you can do. You can do a lot of spectroscopy with X-rays of different energies. You can do other types of scattering on like powder diffraction samples. I think there's now here maybe 30 end stations, so 30 locations where the X-ray beam comes off, and each one of them is perfectly designed and set up for a different type of experiment. So if you look here, I think you drive in, turn to the left, this building right here is where most of the polymer soft matter materials are. If you go around to this end, people are looking at like thin film, quantum materials, and metal oxide, stuff like that. All the bio people are down over here. So each section is kind of based on a different type of science and a different type of experiment that you want to do. Yeah. Yeah. So you need more energy. Yeah, because you're injecting these electrons and you got to get them spinning around and spinning around at a good rate. So the early synchrotrons were definitely a lot smaller and were not as bright. And now we're trying to, now I think they're all this, like the size is nice, but the magnets that we put in and the physics and the engineering that goes into accelerating that beam, that has been advancing very fast. So Greg just got back from another synchrotron outside Chicago, the Advanced Photon Source at Argonne National Lab, and they just went through a full like year-long redevelopment and upgrade to expand and increase the brightness of their facility. So they shut the whole thing down. They went in, they cleaned out all the tubes, they put in new magnets, and I don't even know what they did, to be honest, but they've upgraded and made it now a certain fraction brighter, which now allows us to do more new experiments that we were never able to do before, right? Everything is based off of how bright and how coherent and how strong that beam is going to be, right? How long have synchrotrons been around? Maybe 40s, 50s is when they first started developing them, something like that.
Yeah, well, first they were small, like cyclotrons.
Yeah. Yeah.
They've grown since then. Yeah, so that was the 50s. The 60s when the NSLS-1 was like 1975, I think.
Yeah.
Which is right next to this. I didn't zoom out, but there's another little ring next to it. It's much smaller.
Yeah, so this lab is stuck out way out on Long Island.
The original, one of the original synchrotrons was this, which is just
It's
the
there.
size of this room, kind of.
Yeah.
Yeah, and then the NSLS-1 was a big upgrade, and this thing is.
So the Department of Energy kind of picked this lab to be one of these early places to try and develop this type of technology and do these experiments. So the NSLS, National Synchrotron Light Source 1, is right across the street from the NSLS-2.
Those are all.
It's actually it's this building right here, right, cut up on the top.
Yeah, if it zoomed out a little bit more, you can see there's a smaller.
So it can fit on the inner part of this ring. So when they built the second one, they basically doubled it and expanded it out.
It was big in its time.
Yeah.
I thought it was huge.
People thought it was cool, right? But things change really fast.
Right. That's just showing like the whole place is packed. This is inside the ring and it's just packed with equipment.
Yeah, it's a mess. There's just
all experiments going.
so this is where all these engineers come
Like,
in,
any
right?
one of those 30 beam lines has like probably 6 or 7 instruments.
Yeah.
So it's 30 times 6 to 7.
The engineering drawings like make your head explode. It's absolutely
So you
insane.
go 24 hours a day, cycles, like 4 cycles a year, or they run for 2 or 3 months.
Yeah, so this facility is running 24 hours a day, and the way that you do the experiments is you write a
It's exciting to go to.
Yeah.
You have to work 24 hours.
so you write a proposal with your idea and say, we want to use this experiment to study our material to find out this behavior. And if they
It's
grant
kind
it
of
to
like
you,
when people go to the telescope to, they work all night at the telescope.
oh, yeah,
Not like a user facility.
yeah.
I don't think people know about X-ray user facilities.
Oh, okay.
People know about telescopes.
So yeah, so basically they'll give you a slot of time during their operational hours, maybe 3 days, 4 days, something like that. You go and you just have those 72 hours or whatever to do everything you need to do. So when I was working there, we would pull like 3-4 day shifts where you basically just worked until you fell asleep, and then you'd wake up and then you just keep going. I think I did like 90 hours straight one time, something like that. So no, they suck, dude. I just slept on the floor. One of the beam lines has a couch, which is kind of dirty and nasty, but if you've been awake for 30 hours, you will sleep on it. So This looks what it looks like.
There's like your whole PhD.
Yeah,
So you get- You
every,
can run like, right, for instance, we went to run samples. We ran like 200 samples, but that's like 4 PhDs in one day, you know. It's kind of like the stuff you could do in a year and you see.
so the other interesting thing about this facility, as I mentioned, is we're looking at these detectors and all the data you're collecting. So on top of all the engineers and physicists that are working there, there's an entire team of computer scientists, data scientists, IT managers. I honestly think each experiment you collect about a terabyte's worth of data, which is like you can't even comprehend how much information that is, right? And it's all stored in these correlation functions and in these intensity fluctuations. So in the project, if I hope have some time to talk about it, I think we had on the order of 20 or 30,000 correlation functions that I had to analyze in order to get the actual data out of that. So it's extremely energy data intensive and just a massive amount of investment to do all this stuff. Yeah. Yeah, we are exactly already doing that. Yep. So
Robots. All right, so my son actually works in that area and he does robotic testing and AI to figure out where to do the sampling on an array for industrial development type thing.
So
That's all like well done now.
back in the day when you showed up, you would just guess and be like, oh, I hope this experiment works. And then you do it. And then you get home, analyze your data and see that it was all shit,
Yeah,
right?
so the
So
AI
you will do that?
Yeah,
Okay.
yeah, basically, this is one of the areas where they use AI.
Yeah. So now we're using AI and data and really fast data analysis to get that data out to you as fast as possible so that once you do the experiment, you can look at your data and check and see if it's good.
I mean, it's partly
and
to get
react.
money 'cause it's a popular thing to get. Yeah. Not
It'll help
necessarily-
too.
I mean, your hunches are usually better than the AI, put it that way.
Yeah.
So that it isn't like it, but basically on paper, it looks like, yeah, and especially
Yeah.
to companies, it looks like that's gonna be cheaper.
Even if you are using AI, you personally still need to analyze the data, right? Because it's just data. That's all it is. The AI doesn't know what it means. You're the one who put the material in there. You're the one who's
Yeah.
trying to figure out what the diffusion is, what the dynamics are, right?
Peter did
So
a thing with it, machine learning, AI, and doing this kind of measurement.
did it.
And then he said like, then he compared it with random, like picking
Yeah.
samples at random, and it was even.
Yeah.
Like, so it isn't like it's.
It's not going to save
actually
us. so.
solving a problem. But it is a good way to get money to do research.
So yeah, I'll jump into the experiment real quick. This is kind of what the inside of the instrument looks like. So there's like, this is a hutch. This is where we can do one experiment. This is where we do the XPCS, but there's like 30 or 40 of these all around the beamline doing a bunch of different experiments. So it's this, yeah, so the X-ray comes flying out of the tube here. It gets bounced around, it gets optics spent and perfectly set up for your experiment. And then this is the sample stage right here. The X-ray goes through your sample and then it splays out into this tube. And that's where the detectors are that actually pick it up. All right. So if the DLS experiment, the dynamic light scattering thing you're talking about, that can fit onto a tabletop, right? This giant X-ray dynamic light scattering setup is bigger than this room. It's probably like 30 or 40 meters long.
Probably
something
costs like 50, I don't know, 20 million bucks.
Yeah, dude, you don't even want to know.
Like,
Yeah, this is multi-million dollars of investment right here. And as a postdoc, that's really scary because if you break something, you're in big trouble. So I never broke anything, luckily. But yeah, so there's Lutz. Lutz is the lead beamline scientist at this facility right here. So he's who I worked with when I was a postdoc there doing research. And basically, he's the one who designed, built, and operates and maintains this instrument. So users from universities or companies will come in to use it and do their experiments, but we don't understand all the nuances and all the controls and how to set up the experiments and stuff like that. So there's a team of scientists, staff there that run these experiments with you. And they have,
apply, like you guys could write a proposal.
Yeah. Anyone got a cool idea?
It
Something?
doesn't have to be like cool.
Think about it. It doesn't have to be that cool.
You can get it, possible to do it, especially the APS.
Yeah. So I'll quickly rip through the project I was working on just to show an example. And then if we have time, I can talk a little bit about the papers you guys are going to read. But the project I was working on was actually supported by industry. So does anyone know Henkel? Ever heard of them? Yeah, Henkel makes adhesives. And what they do is they actually have an extrusion setup. It's basically like 3D printing. And no, they're in New, now they're all over the place. Oh, has anyone co-op there before? They're in New Jersey, but so they make adhesives to seal like electronic components and auto parts and stuff like that. And what they do is they extrude out these little road or little beads of their adhesive, and then you can stick the thing down, and then you hit it with UV light, and it cures the two things together. All right. So we were curious about how the extrusion process impacted the curing and the structure formation in that adhesive, right? So the adhesive starts out kind of like a paste. You can squeeze it out of a tube. It's liquid-like. You can move it around. But once you hit it with the UV light, it solidifies into like a super glue, a really hard, stiff object. So our hypothesis was that in the pre-cure state, once it's in the tube, the fillers, there's a lot of fillers in there for rheology modification, for thermal transport, et cetera. Our hypothesis was that in the pre-cure state, while it was in the tube, those fillers would be moving around really fast because they'd be in a low viscosity environment, a liquid-like environment, right? And when you hit it and cure it with the UV, the polymer network is going to cure around it and lock that structure in place, and then restrict and slow down the motion of those fillers, all right? So our hypothesis was that we would be able to track that conversion from really fast dynamics to really slow dynamics in the XPCS. And the reason we wanted to use XPCS is because we wanted to understand what the influence of this deposition process was. Anyone can just throw that in the beam and or do mechanical testing or something like that, but it's really hard to understand how flow and extrusion of the adhesive and how all the relaxation processes with respect to that influence and impact the curing process here, right? So let's actually build a 3D printer that we could put into the beamline. So that is basically shown right here. This is a little zoom up of our extrusion head. So we can extrude that resin out onto this little flat plate right here. The X-ray will come in and hit it from the side, and then we can hit the UV on top of it to cure it and solidify. So basically we're printing just like Henkel does on the factory floor when they're embedding their resin into their adhesive joints. But now we just moved that whole setup and put it into the X-ray beam at Brookhaven so we could do this experiment and now see how the diffusive dynamics or how the dynamics of that process changed as a function of time, right? So this is kind of the idea. If you have an idea, if you want to look at something, there's a pretty big space here. They have a very modular setup where you can kind of bring and put whatever you want in to the X-ray beam and understand your polymer or your materials under different conditions, under different temperatures, humidity, whatever, right? Okay. You guys ready to dig into some analysis? So this is where things get a little tricky. Again, anyone can do this experiment. Anyone can get the data. The hard part is, what the hell does it all mean? So as we were talking about before, you guys learned that there was a correlation function to understand those dynamics, right? But in these processes, these are known as non-equilibrium processes where the dynamics of your material are actually changing during the experiment, all right? So the correlation function is going to look really weird because as you're moving along, the structure is now different. So you can't just correlate back to the original position because later in time, you're looking at something completely different, all right? So when we do this analysis, we can't use that one-time correlation function that you talked about with dynamic light scattering. We actually have to plot the correlations on a 2D plot as a function of any time t1 or any time t2, okay?
Yeah, delta t is the parameter. So when you do the
Yeah.
decay function, delta t is the number you want. But you're looking at that squiggly thing, and delta t here is not the same as delta t over there because it's a curing epoxy or whatever it is.
Yeah, because the diffusion constant is changing during our experiment. When you're doing dynamic light scattering, you're assuming my system is at equilibrium, everything's nice and happy. You're just saying, what is the diffusion constant of this system material, right? But in this experiment, our diffusion constant changes as we're taking data as we move along. So what we get are these 2D plots that show the correlation as a function of any time t1 and t2 during our experiment, not just t0, okay? So if you were looking at a plot like this for an equilibrium system, Where's your good marker? Basically, the way the experiment progresses along this diagonal right here, we call this the aging time. So this is the beginning of our experiment. This is the end of our experiment.
That's when T1 equals T2. So it should be that they're perfectly correlated. 100%, that would be number value of one.
Yeah, we define it as actually an average time between T1 and T2. So that's just the average time along our process. And if you're at perfect equilibrium conditions, these will be symmetric on each side during the entire experiment. Basically saying my correlation doesn't change as I go along my experiment from one point to another. The dynamics are the exact same at every point, all right? Do you guys notice a difference between this bad drawing I drew here and some of the data we have here? What's happening in this picture here? Splaying out, right? So the decorrelation process on either side is evolving and changing as we go along with our experiment. So in order to analyze this data, what we do is we go in, and I've drawn these little slices right here, these purple lines. Those basically go in and say, hey, let me just assume that I started my experiment at this time during the process. So 10 seconds after I started looking at the dynamics, or 15 seconds after I look at the dynamics. And what we do is we slice along this right here, and we calculate a new one-time correlation function, assuming that point was the beginning of our experiment, all right? And basically you can see if you slice along these corners, you can see it goes from dark to white really quickly. That's this curve right here. So the one-time correlation function there, it decorrelates very fast. It's all correlated, and then the dynamics are moving around so quickly that all of a sudden the picture changes completely. And that's where you have this very quick transition from high intensity or high correlation to low correlation. And as we move along these diagonals, you start to see that the high correlation persists for longer and longer and longer, and then eventually starts to decay. So this experiment right here is showing that as we measure at different aging times, the decay of our correlation function is growing and growing and growing, getting slower or faster.
So it seems to have bursts, like you have, there's nothing, then there's a little one, then there's another burst. It's like stages in a rocket or something.
Maybe, I don't know. Yeah, but a lot of analysis you could do with that. So there's something funky going on here, right? But the key thing is that the dynamics are slowing down over time. Remember, that was our hypothesis. We said if we deposit this thing and we cure it, yeah, we're just shining UV on it the whole time. So if the UV is on there and it's cross-linking the network, we should be seeing this system slow down in time. And that's exactly what we saw when we analyzed the data. But like I said, this here is thousands and thousands of correlation functions that we need to analyze, plot, and then fit. You fit it with an exponential function to get that relaxation time out of it, right? Yeah, Chris.
The computer that does all these calculation functions for you, or is it
Yeah,
just
so
manual?
when I was there, it took about 15 minutes to compile and plot the whole thing out. So you had to sit there and wait. I think it's a little faster now, but yeah, you can see kind of really broad overview. Essentially what we get are these patterns, and you just kind of have to look at them and be like, yeah, that looks all right. I'll go and analyze it later. So once we saw these patterns, we were really excited because we knew that there was something interesting in there. And then I had to go home, sit on my computer and analyze and plot everything and do all the fitting and stuff like that. So basically what we're trying to do is at least get a general sense of what's going on, but the actual quantitative information, that takes a little bit more time to do because there's a lot of fitting parameters here. We have to make sure it's following and has a good fit and all that kind of stuff. So, yeah. So real quick, what we were finding in these experiments, remember how I talked about that diffusion earlier? These dynamics did not follow diffusive dynamics. So if we took that relaxation time, here I'm just plotting the inverse of that, the rate. If it scales with your scattering vector q squared, you got nice Stokes-Einstein diffusion. But when we took the data, we took that relaxation time and we plotted it as a function of just Q, right? So that's a linear relationship between the two things. So that no longer explains diffusive motion. That actually explains linear ballistic motion. So we were just basically measuring, if you take this slope right here, it's essentially a velocity. So it's how fast is this particle moving from here to here. And that was really interesting because diffusion is usually the thing that you assume, right, for just kind of Brownian behavior of a particle moving around. But in our filler system, the polymer matrix was kind of so thick and so strong that it restricted that diffusive motion and caused all the particles to kind of move in this collective linear behavior.
Well, I mean, all right, so particles would fall in something like a polymer chain, and on a small enough scale, they have steps. So there's a persistence length. In fact, the word persistence length came from gas atom motion, because the steps, the linear steps. are
Before it
around
forgets
the
where it's
atom.
going. Yeah.
So this is what you're within the persistence length of the motion of the particle, or the gas.
That internal length. Yeah.
That's defined by the properties of the motion of the particle, like the viscosity. You can define that number.
Yeah.
So if you look at a small enough cube, you're gonna see ballistic motion, because you're seeing within the persistence
Yes.
the same motion.
So that's kind of what we were looking at. If we did light scattering on this and zoomed out to much larger length scales, maybe we would start to see that diffusive process adopt. But because we're zooming in on the the nano scale, we saw these kind of really fast, abrupt movements all kind of correlated and collected together. But the cool thing about this was it allows us to quantify the dynamics at that small length scale. So this key thing we wanted to get was this VP, this particle velocity. And what we then did was we plotted that particle velocity as a function of time. And that was a way for us to infer how the curing process was happening, right? So each one of these curves is a different intensity of the UV. So the one, I'm colorblind, sorry. The blue one's up here, that's with no UV. So that's kind of just the natural relaxation. If you just let this thing spot out and kind of let it just flow on its own, that has some characteristic relaxation process. But as you go to the green, the orange, and the pink, we see that that velocity decreases faster and faster and faster because we're putting more UV onto it and we're restricting and locking up the structure in a quicker amount of time.
So is that the velocity versus time is the acceleration, but it's a log part.
No, so it's not acceleration, it's just what the velocity of that particle would be if you looked at it at that time.
No, it's decelerating because it's dropping. So it's a deceleration, right? In other words, if this was a linear plot, it would be the slope of that would be the deceleration.
Yeah, kind of.
DVDT.
Kind of, yeah.
Okay. Anyway, all right.
But these are like just equilibrium. You're kind of just saying at a snapshot at any time what's going on.
Yeah.
Anyways, moral of the story is that in the early stages, when you have the UV on, obviously the thing solidifies and cures. But we left the experiment on for like 10 minutes afterwards, and we saw the dynamics continue to evolve. So what this told us is that when you're doing additive manufacturing or 3D printing, and you print something, you move along and you print something else, right? And you just leave that thing behind. You say, oh, I'm done. Cool, whatever. I'll go print another part of the structure. That structure is still evolving even after you've deposited it and quote unquote cured it. We saw the dynamics continue to decay down even after we turned the UV off and went to some other location. So this indicated to us that you need to be really careful about when you're printing something. You can't just set it and forget about it and move on to the next layer. That material's still changing, still evolving. It still has non-equilibrium properties even 10 minutes after you've printed it, right? So yeah, so that was kind of our key takeaway. And that was important for Henkel because they want to speed this thing up as fast as possible, right? They want to put that down and be like, oh, we're good to go. And this data showed, under those conditions, under this type of print process with these UV, you have to wait about 10 minutes until you've reached a steady state or an equilibrium structure formation in your material. And if you wanted to then print another layer on top at different times, you would have to deal with that because the whole thing would keep evolving. Yeah.
So could you with this data figure out like what time like to hit 95% like?
Exactly. Yeah. So that's what the second paper we wrote was on. It was how long do you wait before you come around and print another layer on top to build up that structure? So at some point, you will have enough structural rigidity where you can maintain and take on the next layer, and it'll be able to support it. But what we found is that if you look in that bottom layer, when you lay the top one on top, it shakes around. It actually feels the weight of that top layer, and it breaks the structure momentarily and then goes through another kind of reorganization and relaxation process. So all of these structures, you may just see it and be like, oh, I printed a solid part, cool. No, the structure is still alive. It's still transient. It's still evolving throughout the entire 3D printing process as you're building up some big structure. So that was really exciting from this research, and we're trying to now look at other materials like polymer melts, polymer resins, stuff like that, to see if that same type of behavior shows up as these curable epoxies. Yeah.
I just have a quick question, if you might have some insight on, like, if you were extruding like a plastic tube or something, would it have that same like type of idea of cool down time, or?
Yes, definitely. So I'll come back to you there. Some folks are doing experiments right now trying to investigate that. It's a lot harder to do with polymer melts because the structure is a lot more complex. You've got polymer crystallizing, you've got additives in there, stabilizing, doing all this stuff. So when you get the XPCS data, if you were to measure that, you're just gonna have a ton of stuff, and it's really hard to decouple what that is coming from. But there's been a lot of really cool simulation and thermal imaging on polymer melts to show how that structure cools down in time. And also with that type of technique, when you're printing a polymer layer or you're extruding something, it cools down. If you put another hot polymer layer on top of that, the heat is going to transfer and heat up the bottom layer, right? So you thought that thing was crystallized and cooled down. Now it gets an injection of heat. It gets happy, it rearranges, and then it cools down as well. So every time you're doing this, you're injecting new stimulus into the system. And the XPCS allows us to toggle or to tune in and see what those dynamics are and how they're evolving through time.
We have to kill a lot of time, I think, but.
Oh, didn't even get to the papers. Okay,
All right, yeah, no, it's good. I think what you said.
that was impressive.
perfect.
So
Okay, yeah. Yeah. So why don't we thank him for showing up. Good checking for our time, thanks for doing that. Pretty good.
yeah,
I think it was plenty stuff. I mean,
okay.
there's a lot to learn, so
Yeah.
it's good. Yeah.
The home-
I thought 6 slides wouldn't be enough. That's why I threw in the other things, but actually it was plenty.
That's good.
Yeah,
The homework was hard. So
yeah, that's good. Art is good. My pens, I grabbed back because these are the only ones I have. You can have your black one, it doesn't work.
Yeah.
But, so, yeah, thanks for doing that.
Yeah.
It's pretty good. It's good hearing you talk about it. I don't know why Alan Sick didn't show up. It's like he's the one who's doing that. Oh, is he?
Yeah.
Oh, okay. Yeah, so do the selfie thing for the 20 point, whatever, and you can also get the question point.
What's up, man?
right, you know.
Talk about that with mechanics or?
it has some fluid mechanics in it. We talked about the
So if I'm trying to open homework 9,
Yeah.
it just automatically opens homework 10.
That makes sense.
All right, sorry, I messed it up. Yeah, I'll fix it actually. I can't do it. I'll do it in like 2
And
minutes.
same goes for the papers as well.
Yeah,
So
that was my
if I'm
project.
opening the paper.
So
it
the
is
story,
opening
I
these
collected all the data. from
Okay,
the
I did it really late
And
last
then-
night. Yeah, I messed it up. Sorry, I'll fix it.
Just add it on when I
Let's see, let me just,
So, yeah. But yeah, we got there's probably 2 or 3 papers from that type of stuff we did. And then, yeah, and then Greg just went back, a couple of weeks ago and did 2 more experiments, so we have some more data to look at and analyze.
What that all costs?
All free, it's paid by the taxpayers.